share with you some of the lessons around how to handle an SLO that has become broken and what to do to recover from it, both technically and socially. My name is Liz Fong Jones, and I'm a principal developer advocate at Honeycomb, where I work with the site reliability engineering and observability communities. So, today we're going to talk about four things. First of all, we're going to talk about what even is a service level objective and why should you have one. Secondly, what changes to your development processes might you need to make in order to accommodate that? Third, how do you actually deal with situations when your SLO has gone wrong? And fourth, what can you take away and apply to your own systems? So first of all, let's start defining a service level objective and its companion, the service level indicator. So this concept was introduced to me about a decade and a half ago when I started working at Google. But for those of us who are outside the Google ecosystem, it turns out that there's been this robust iteration of the literature since Google published the Site Reliability Engineering book with O'Reilly. In short, you can learn more in Chapter 4, but the idea is that we want to quantify reliability and describe what users actually want, not necessarily your service level agreement in a contract, but instead something that helps your operators maintain a service standard for your customers in an actionable manner. And that doesn't mean setting 100% as your goal, because that's not actionable. If you have a single error, that's going to throw your entire error budget forever. Instead, a service level objective should be set to something reasonable and meaningful. For instance, that you might want to have 99.99% availability over the course of a month or over the course of a quarter. So, in the context of Honeycomb, we maintain many different service level objectives corresponding to the user journeys that our customers expect. And specifically, we're a company in the observability space, which means that we have to ingest telemetry from our customers' software systems. And then we allow almost index-free analysis of that data because we're actually indexing everything. And then we enable our customers to query that data in real time. So in other words, customers depend upon us to debug their outages when they're in turn having outages. So it's important that we have as few outages as possible and that data is performant. So what does performant data mean in the context of observability? For us, it's three crucial ingredients. First of all, that if someone wants an overview of their data, that they can get to the Honeycomb homepage relatively quickly and see their rate, error, and duration graphs. Secondly, our customers need to run arbitrary queries of arbitrary complexity, and they have to return reasonably quickly. Not necessarily as quickly as the canned queries we have on the homepage, but we want it to take no longer than the amount of time that it takes to take a sip of your coffee in order to see results, rather than waiting minutes for a query result to come back. And then finally, it's important for us to ingest the vast majority of your data and very, very quickly within milliseconds, because it sucks to have your metrics go south and have to wait a minute or 5 minutes to see whether they've recovered. We want you to be able to see the results of your data changing instantly. So these are some of our service level objectives. This is the one that pertains to the ingest that I talked about, where we expect that 99.99% of events that are ingested into our system are successfully ingested with less than 5 milliseconds of latency over a trailing 30-day window. Now, that would mean if we had 100% outages, only 4.5 minutes of violation per month, which is not very much time to respond. So in order to actually achieve that result, we have to use gradual degradation and graceful degradation instead. So that in the event that there is a problem, and we're degrading, say, 1% or 2% of requests, what we have is not 4 minutes to respond, but 400 minutes to respond to solve that service degradation. So that's how we actually aim to achieve this result with keeping a service level objective reliable and also achievable. So once we've kind of graphed our SLO, we have an idea of how are we doing against that target and what are some of the factors that are causing us to burn through that error budget. How do we design our development cycle around that? Well, for us, it involves continuous integration and delivery. What we do is we design around feature flag deployment as well as observability-driven deployment. That means that when we write code, we build feature flags around it, and also we ourselves practice observability. We add rich trace spans and trace attributes using OpenTelemetry in order to make sure that we can understand what feature flags are causing impact to our users so that we can only break a small fraction of them at a time in the event that something bad does get out. We also have very robust tests that verify that everything is safe to roll out to at least our dog food environment, which is where we observe our production environment. And from there, it's progressively deployed through more and more environments until it reaches our customers, and then it gets feature flagged on to a majority of customers. So we mean that we keep our build green. Our build takes less than 10 to 15 minutes to run, and therefore no one feels tempted to bypass the tests. And when people hit the green merge button, it gets automatically rolled out to production. And in the event that there is a problem, we actually check that our service level objectives are met before we promote things to higher and higher environments. That way, we can ensure that we are able to catch the leading edge of a potential problem in production. But the most important thing that we do is we use the output of production telemetry to understand whether or not our builds are working reliably and successfully. There is no substitute for production. The joke is that everyone tests in production whether they like it or not. It's just a question of how good you are at it. So for us, we then generally tend to have our experiments work, but not every experiment will succeed, and that's okay. According to the DevOps Research Assessment Organization's surveys and the Accelerate State of DevOps report, elite performing organizations are able to remediate and repair production outages in less than half an hour. They don't necessarily have a lower change failure rate. So for elite organizations, their change failure rate ranges from 0 to 15%, which is the same as high or medium performing organizations. So how is it that we are able to recover from failures quickly? I'm going to talk through 3 instances in which we blew or nearly blew our SLO and what we did in response. So first of all, let's talk about our Ingest service outage. So as I mentioned, this is our highest traffic service. It's a stateless service that basically acts to shovel data into Kafka. And originally, in 2019, it was primarily using compressed JSON. And in 2020, it was primarily using compressed JSON. But in December of 2020, we needed to switch over to using gRPC in order to support OpenTelemetry. So in order to do this, we were working on adding a custom port on which to bind to the gRPC worker. And we wound up pushing code that worked fine in development, but did not work successfully in production. And scale up of new instances was blocked, even though we automatically ensured that we were not going to continue rolling out the new build. We still had a problem in which latency increased because the traffic increased and our workers were not spinning up. So this took more than 10 minutes to remediate, and it blew our SLO. And this wasn't just a 1% degradation, this was a 50% degradation of all service. So as a result, we could have chosen 3 different paths. First of all, we could have chosen to freeze all deploys. And some people who take a very rigid interpretation of the Google S3 book say that that's what you ought to do. But actually, what the Google S3 book says is that you should freeze all feature work and that you should work only on reliability work until your error budget is fixed. But we're a small, scrappy startup. We can't necessarily afford to do that. One other option that we considered was delaying the launch, except for it was implicated in a partner launch in which we are going to be announcing support for OpenTelemetry alongside a number of other partners. So instead, we chose to mitigate future risk going forward while also recognizing that we'd already burnt a substantive fraction of our error budget. So what we chose to do was we chose to reduce risk by using separate deployments and separate routing in order to almost do a blue-green deploy. And that enabled us to safely iterate on repeatedly pushing a feature branch while continuously rebasing that feature branch to make sure we didn't drift out of sync too quickly. So that's how we wound up ensuring that we could recover from an outage of our critical data ingest pipeline. But let's talk next about what happens once data gets into the ingest pipeline in Kafka. So Kafka's number one goal is to provide durability. It is the stateful service so that Shepard can be stateless. And decoupling the components provides safety, but it also does add new failure modes, because Kafka is a piece of software that we did not write in-house. And therefore, it's something that we're always looking to benefit from the expertise of others on. So in 2021, we were looking to migrate onto Confluent Enterprise Platform, which is a distribution of Kafka. And we thought that we could benefit from tiering data to S3 that was less frequently accessed. And if we were doing that, we thought that we may as well migrate to instances with smaller on-disk storage that had a more modern hypervisor. Now, unfortunately, when we changed multiple variables at once, we actually broke things in a way that was not necessarily degrading our service level objectives, but instead was making our service too brittle. It was very painful for human operators to need to manually rebalance things in order to keep the system from becoming saturated and overloading itself. Because we are trying 3 different things at the same time, we ran out of network, we ran out of disk IOPS, and lastly, we actually got to the point of tickling a bug in the Nitro hypervisor that caused instances to spontaneously reboot on us. So this thrashing didn't impact system stability, but it impacted the stability of the lives of our humans at Honeycomb. So we were eventually able to roll forward once there was a slightly more battle-tested deployment of the AWS Graviton2 processor coupled with instance storage rather than using elastic block storage. So the lessons that we learned here were that even though we were aiming to increase the scalability and reliability of the system, this change had a paradoxical effect in which we actually negatively impacted our team. So this is a reminder to us to reinforce that it's okay to wave the flag and say, I don't think that this is safe to proceed, or I need someone to relieve me on on-call, or please make sure that Honeycomb buys me dinner so that I don't have to worry about cooking dinner and firefighting at the same time. And in the end, we backed out the change. We waited about 8 months, and then we were able to successfully migrate onto the AWS Graviton-based instance storage services. But we were able to do just one thing at a time and get the tiered storage change done without further burning out our people. So now lastly, let's talk about Honeycomb's querying service, Retriever, which reads out of Kafka and serializes the data to S3. And once the data lives on S3, it can be queried massively in parallel from AWS Lambda. So what we wound up trying to do here was we were trying to ensure that we could keep the AWS cost of Lambda in check. Because it turns out that, while it's great that you can query 30,000 S3 files in parallel at the same time, it also can be a little bit terrifying to query that much and discover the AWS Lambda build. So we were aiming to try the ARM processor architecture with Lambda in order to improve the efficiency of our querying. But we deployed this with feature flags, and we discovered pretty quickly that we are breaking both our query latency SLOs, as well as some of our cost metrics when we initially turned it on in November, shortly after the release of the feature. So we were able to very quickly revert this within a matter of seconds in order to preserve the stability of our system. So this is an example of everything working as designed. Our SLO blew, or indicated that it was going to blow if things would have continued for multiple hours, and we were able to revert and have a look and proceed more carefully and thoughtfully. And the good news is that because we are able to control this with percentage-based feature flags, we're able to scale up from 1% to 10% to ultimately 30% once we gained more and more confidence in the code. And today, actually, we're running 99% on AWS Lambda on the Graviton architecture. So experimentation is okay, outages are okay. The question is, how do you manage it? In order to be both fast and reliable, you need to design for reliability through the full lifecycle of your application. Feature flags on your application code can keep you within SLO most of the time, and even when they can't, you can find ways to integrate feature flagging techniques into your infrastructure operations, to use blue-green deploys or other rollback mechanisms in order to segregate traffic and ensure that you always have something that you can safely roll back to. When you discover and spread out risk early, it prevents you from incurring all of that risk all at once. But black swans happen. You can have incidents like SSL certificates expiring, DNS, you can have log4j. Your SLOs are a guideline, not a rule. At the end of the day, they're a tool for you to communicate about reliability and make your services better. So by discovering those hidden risks early and often, you're able to plan for them and proactively manage them. So when you make experimentation routine, it makes it possible to try things and increase the speed of innovation in your team while hopefully having the queries flow and pagers mostly staying silent. We're all part of sociotechnical teams as customers, engineers, and stakeholders. When you have outages and failed experiments, it's not an occasion to blame people. Instead, it's an end-scheduled learning opportunity that you should try to get the most out of. We have to discuss between different people and teams what our expectations on reliability workload and on-call workload in order to make sure that we're balancing keeping our teams healthy, our customers happy, and the bean counters happy. DevOps is just talking to each other. We all want to put our customers first, so let's figure out how to make that happen sustainably in the long term, rather than burning ourselves out chasing unachievable numbers of nines, or by following too rigid of processes. So that's what I have to share with you today. And if you're interested in any of these topics related to feature flags, observability, and high-performance engineering, have a look at our new Observability Engineering book that was just published a few weeks ago that you can get a copy of for free at the link on the QR code on the screen now. And that's all that I have to share today. Thank you very much, and I'll see you around for Q&A.